All right, so in this case, we need to now figure out how much mass was lost. So our products are going to have less mass. Our products here are going to have less mass than our reactant. So we need to add up the masses of our products. So radon 222. This is all on page 8 in your data booklet. Okay, these are the masses of these different isotopes. And you can see it has a 222. So this mass is 222.01757. Don't worry about the units or anything like that right now. We're going to add that to the mass of the helium. The helium, here we go. It's 4.00151. All right, and then we have our radium 226. That's this, radium 226. You got to watch those mass numbers. Make sure you got the right one, and it's 226.02540. All right, so we want the mass of our products. Mass of our products. And this is our mass of our reactants. And so we're going to take the mass of our products minus the mass of the reactants. So we add our products all together. So we're going to go 4.00151 plus 222.01757. So our mass of our products here is 226.01908, and then we're going to subtract the mass of our reactant here, which is 226.02540. You can put that all in your calculator and see what you get. And you should get 0.00632. It's a negative number because we've lost that amount of mass. Now, this isn't the exact number because we got to watch for this here, the units. So what are the units? So our actual mass that is lost, or the change in mass, is equal to negative 0.00632. And then we're going to use these units that are here, times 10 to the negative 3 kilograms per mole. So we could have put these units in at the beginning before we did all the adding and stuff, but it's so much easier to throw it in right here at the end. So we've just found our change in mass. Now we can use Einstein's equation to figure out what happened to how much energy did this mass form. We lost this mass. It didn't just go nowhere. It turned into energy. So our change in energy is equal to our change in mass times the speed of light squared. So our change in mass is negative 0.00632 times 10 to the negative 3 kilograms per mole. Actually, the moles go away because we multiplied those out. And then our speed of light is 3.0 times 10 to the 8. If you forget, that's also from our last unit on the electromagnetic spectrum page. What page was that? 4 or something like that? Okay, so square this number, multiply it by this mass, and see what you get. So when you square that speed of light, you should get that number. Then you're going to just multiply it by our negative 0.00632 times 10 to the negative 3. Okay, and so when we multiply these together, we should get negative 5.688 times 10 to the 11. All right. And from back in unit C or B or whatever unit that was, we know that energy is measured in joules. So that's in joules. So you have the answer keys right here. Make sure you go through this, do this on your calculator so you understand how to do that calculation. Definitely a little tricky if you haven't practiced it. All right, I'm going to do one more example, even though there's a few more in the lesson, but we'll do one more, and then you can use the answer keys that are provided to check your answers on the last two. Calculate the energy released by the alpha decay of polonium-210. So because they don't give us anything about the mass, we can't just hop to Einstein's formula because we don't know what the change in mass is. So we have to figure out what the change in mass is for this nuclear reaction here. So let's write out polonium. So polonium is, let's look that up on our periodic table. You can also find it on page 8. If you look up polonium-210, it'll actually give you the isotope notation for polonium. So polonium is PO, and it's 210, and the atomic number is 84. And it's going through alpha decay, which again is a helium atom. Oh, why do I keep putting a 0 there? I did that last time too. And it's a 2. Okay, and then let's see what the leftover is. So we're going to have a atomic number of 82. 82 plus 2 gives us 84. And then 206 plus 4 gives us 210. So our equation is balanced here. If we look up 82 on our periodic table, we will see that gives us the element of lead, Pb. So polonium is decaying into lead. Now let's see how much energy or mass is lost in this process. So we're going to find the mass of the products, and then we'll subtract the mass of the reactants. So the mass of products and the mass of reactants. Let's look them up. So these are all looked up in our chart on page 8 again. So look them all up and see if you get them right. Okay, so we've got lead-206 with its mass from the chart, helium or alpha particle with its mass, and the polonium-210 with its mass. We're going to add up our products first and then subtract our reactants to find the difference. Okay, so our two products add up to 209.97601, and then I'm going to subtract that from the polonium. And that gives us a mass change of 0.00685, and that's negative again. We're losing mass. And remember, we go back and we just check our units, and our units are all going to be times 10 to the negative 3 kilograms. All right, so our change in mass, but we want to know how much energy is released. So this amount of mass is lost. So what does that turn into in energy? We're going to use Einstein's formula. Equals change of mass times the speed of light squared. So our change of mass is negative 0.00685 times 10 to the negative 3 kilograms. Our speed of light is still 3.0 times 10 to the 8 meters per second squared. So square this and then multiply by this number and see if you get the right answer. All right, and our answer is negative 6.85 times 10 to the negative 6 joules. So that's how much energy is produced when that mass is lost in this nuclear reaction. So if we can harness that energy, that's a lot of energy for just 1 mole. That's a lot of energy that we can keep and use again. All right, so there are a couple more questions that you can try out, and the answers are there. If you're having any problems, let me know and we can go over this together.